Okay, today we'd like to do pressure below a fluid, a very important topic in the study of fluids. So before we start, I'd like to show you a commercial that maybe you've seen before, and I want you to focus on what this person is saying and doing, because you'll see that they're actually trying to trick us and deceive us about their product.
Hi, Phil Swift here for Flex Tape, the super strong waterproof tape that can instantly patch, bond, seal, and repair. Flex Tape is no ordinary tape. Its triple thick adhesive virtually welds itself to the surface, instantly stopping the toughest leaks. Leaky pipes can cause major damage, but Flex Tape grips on tight and bonds instantly. Plus, Flex Tape's powerful adhesive is so strong, it even works underwater. Now you can repair leaks in pools and spas without...
Okay, so I'm going to pause it there because all the key things that he deceived us about have already happened. What are they? Well, we got to wait a little bit. Let's see what we learned yesterday in lab. So yesterday in lab, we took a pocket lab and we put it at the bottom of a cylinder, and we put different amounts of fluid in the cylinder, and we monitored the pressure. We let it run for about 10 seconds, and we got our average pressure at that location over those 10 seconds. We then added a different amount of water, this time a lot more water, and we could see that the pressure rose significantly from where we started. So right away we could see that greater depth gives us greater pressure. That's a key idea. Greater depth gives us greater pressure. You know that if you've ever thought about scuba diving or a submarine or any other experience in the ocean, the farther down you go, the greater pressure you feel. But what kind of relationship is it? Well, when we graphed it out, we found that it was a linear, not proportional, a linear relationship with a distinct y-intercept. Okay, I wanted to show it to you in real life, so I took a real cylinder, I put a pocket lab in a plastic bag, and I poured water over the pocket lab to fill the cylinder. If you watch, the red line represents the pressure, and you can see as the water level goes up, so does the pressure. And again, when all's said and done, we get a graph that looks like this. This is our important equation, and believe it or not, it just comes from the simplest of equations, y equals mx plus b. Y is pressure. We should call it total pressure. This pocket lab measures the total pressure at that depth. Slope, 85/70. X, depth. The letter we're going to use for depth is actually H. It's the height of the water above the pocket lab. And then we have our y-intercept. And what is that y-intercept? That y-intercept represents the pressure the pocket lab would experience if the depth was 0. So why is it still experiencing a pressure at a depth of 0? Because of the atmosphere. So that y-intercept would represent atmospheric pressure. So total pressure, atmospheric pressure, depth, that leaves the slope. What is that slope? What determines that slope? What determines how quickly the pressure goes up as it gets deeper? Well, it turns out there are two factors, and hopefully you can guess what they would be. One, the type of fluid. Two, the strength of the gravitational field where this fluid is located. So once again, the slope is determined by the density of the fluid and the gravitational field where the fluid is located. They are the two things that determine how much pressure is going to be created by that fluid. Okay? So if you had salt water, you'd put a density of 1024, and if you were on Earth, you would put 9.8. You then multiply by the depth. Make sure your depth is in meters, and then you would add to that atmospheric pressure. Make sure you're working in pascals, because pascals is the true unit for pressure. All right? Notice, something that's not a factor are things like the length and the width of the container. The only thing that matters is how deep the container is. So it doesn't matter whether or not it's a rectangular container, a cylindrical container. It doesn't matter if the cylinder is wide or narrow. All that matters is the type of fluid and the planet. And the depth, obviously. Okay? But the shape of the container does not matter. The size of the container doesn't matter. Yet, when this guy did this demo, he used a giant container filled with tons of water, and people are going to look at that and think, wow, this tape is able to hold back a lot of pressure. Well, in fact, if you look, it's not a lot of pressure at all, because he put the holes almost at the very top, a couple centimeters at most below the fluid level. So the pressure here, even though it looks so impressive, the pressure there is almost nothing. It's almost at atmospheric pressure. So maybe the product is good, maybe the product is not, but this is a very deceptive advertisement. You'll notice even at the shallow depths that he used, that you'll see bulging taking place on the flex tape. Okay? Yes, it does flex. Yes, it does hold it back. But what would that look like if you tried to have a greater pressure than what he's actually showing it? The other thing he did is he made it seem like it was an amazing thing that it worked from the inside of the tank. But if you think about it, it doesn't need to be sticky at all on the inside of the tank. The water itself is going to push it up against the plastic or plexiglass side. Okay, so maybe the product is good, maybe it's not, but these demonstrations look much more impressive than they actually are. What do you do if there's multiple fluids? So in this case, you'll notice that you got the atmosphere pushing down on the top. You got the orange fluid pushing down. You got the green fluid pushing down. And you got the cyan fluid pushing down. And if I want to know how much pressure it's making on the bottom, I simply add those pressures all together. So when I do total pressure, it would be pressure 1, pressure 2, pressure 3, plus the pressure from the atmosphere. So these three are the pressures from the three different fluids in that graduated cylinder. Density of the fluid 1, gravitational field, height 1. Density of fluid 2, gravity, height of fluid 2, and so on. Make sure you realize height 1 is simply this height, the height of the fluid. Don't go all the way to the bottom, just do the height of that actual layer. This would be height 2, and this would be height 3. Add them all up, you get your total pressure. Okay, let's see this in real life. So I have a metal cylinder inside a tank of water, and if I wanted to know what is the pressure on the top part of that cylinder, all I would do is see how far below the fluid line it is. I would use the density of the fluid, and I would use the gravitational field. The deeper I let it go, the greater the pressure it's going to experience. If I pull it all the way up so the top is actually out of the water, now the only pressure it's experiencing is normal atmospheric pressure.